Hi, I'm Gary, and I want to show you how I use Cloudy. So in this video, we're going to be thinking about how temperature of the gas is set up. We've been talking about temperatures. We bumped into it a few times in Cloudy output. What actually is it, and how is it computed? What does it depend on? How does it change the spectrum? And to close the loop, how can we use temperature-dependent properties of the spectrum to figure out things that astronomers actually care about? To begin with the real problem here. This is the root problem in this whole field. We're dealing with an extremely highly non-equilibrium gas. And one of the vexing problems is we're dealing with actually a really hard vacuum by laboratory standards. Even dense regions in astronomy are pretty good vacuums. So this scale compares a broad range of environments. Densities are given along the top 10 minus 4, 10 to the 20. That's about the same range we've played with cloudy. Several classes of nebulae or of objects are shown along the axis. So we see here the typical galactic astronomers, extragalactic starburst galaxies, you're working at densities that are really good laboratory vacuum. And so the problem with that is that this gas is not in contact with itself because this is such a vacuum that there are very few particles, collisions between particles or constituents in the gas. It's a way to think of it. So the populations of levels ionization and the spectrum is determined by microphysics, not by thermodynamics. So this region cannot be understood in terms of equilibrium thermodynamics, one temperature in a Boltzmann equation, that kind of thing. Instead, we have to fall back to what's going on, the microphysics. And so this is photoionization equilibrium. So what we have here in the lower left is a plot of some SEDs. The wavelength is in microns. So visible light's on the extreme right, and on the left is ionizing radiation. The red bar indicates the amount of energy needed to photoionize hydrogen. So everything to the left on this plot can photoionize hydrogen. What's shown is three SEDs that are available in cloudy. The black one with a lot of structure is a pretty good O star SED that you might want to use for a galactic H2 region. The much simpler red SED is for a hotter planetary nebula nucleus. So this is 120,000 Kelvin. The O star is something like 38,000 Kelvin. And then finally, the blue line is an AGN spectrum. That's a non-thermal continuum. So what happens in the gas is one of these ionizing photons hits a hydrogen atom, and that photoionizes it, so it breaks apart the atom. It takes 13.6 eV to change one hydrogen into a proton plus electron. So if this ionizing photon has 20 eV, then there's 6.4 eV left over once the photon energy is broken apart, the proton plus electron. So that's the kinetic energy that the photoelectron has. So the photoelectron has a great deal of energy, and that's the residual energy of the incoming photon. And then the work that Cloudy is doing in codes like it, you're taking the atomic data to try to convert this into emission lines. So this difference is in Osterbrock is called a capital G. It's called the gas heating. So heating in this field is anything that adds kinetic energy to the gas. And so the photoelectron has a great deal of energy and it shares it with the other electrons, so it heats them up. Then the electrons, the free electrons, the main electrons, collide with other atoms, let's say O3, create an internal excitation. So the thermal energy of the electrons can be converted into light and lost back out. So what's happening here is starlight coming in creates a photon that heats the gas up. The gas then collides with other things, producing emission lines that cools it back down. Let's quickly go over the life history to see another part of this, why this problem is challenging. So this is an energy level diagram where you have principal quantum number and angular momentum. So this is for hydrogen. The energy is the energy relative to the ionization potential. So this is hydrogen. So this would be the energy in Rydberg's, a funny atomic physics unit. So one is exactly the amount of energy needed to tear away an electron from the ground state. So if we have an ionizing photon come into the system, which with the amount of energy shown in red, the first 13.6 eV of energy goes into tearing the electron away from the atom. And then there's an amount of energy left over, which is the difference between one and this, whatever the photon had. And this is kinetic energy given to the gas. This is then shared with the other electrons. The yellow band represents what was called thermal electrons. So those are the electrons that have the electron temperature you can measure with some line ratios. So for an ionized cloud, it's typically something like 10,000 degrees. And eventually, the electrons the word is recombined, they'll be captured at bound level and work their way back to the ground state. So some jargon that comes with this. The yellow band is what you want to assume everything is there. That's the thermal electrons. And so we'll be seeing different ways to measure temperature of electrons, and we've seen cloudy predicted with the zone results. This photoelectron uh, has a great deal of energy and is in some literature is referred to as a superthermal electron. So that means much more than thermal energy. So that's the new heating going into the gas. Just to put timescales on here again, like the density scale would put it in perspective. For the central regions of the Orion Nebula, that's getting fairly close to the O star, the ground state, we have electron in the ground state, it will sit there for about a day before a photon strikes the atom, it absorbs the atom, and it goes into becoming a photoelectron. So if it picks up a high energy photon, 30 eV or something, make up your number, it ends up as a super thermal electron with much more energy than thermal electrons. And in a time scale of about a second, it will share its energy with the other electrons. So this is a very fast process. So we normally neglect the superthermals and we speak only in terms of these thermal electrons. They sit up there as thermal electrons for about a year before they have a near collision with a proton, and then it becomes captured in these bound levels and works its way back down. These levels have lifetimes of 100 nanoseconds. They're very, very short-lived. So it goes back to the ground state and the whole process starts again. So you can see there's a fantastic dispersion in timescales ranging from 10 to the minus 7 seconds up to a year. So this is can be a very, very non-equilibrium situation. We're going to be talking about heating the gas and what creates the temperature we see. And go back to our SEDs and think about this heating, this photoelectric heating. So you take the incident radiation field, so pick some energy down here, a high energy photon. If it's absorbed by hydrogen, uh, the photoelectron has a certain amount of energy, and that's given by h nu minus this 13.6 eV. So what we've done here is average h nu minus 13.6 eV over these three different radiation fields. So this gives the mean photoelectron energy. So you can see for an H2 region, the photoelectrons are not hot. They're 50,000 degrees. The gas temperature, typically H2 region, will be, depends on metallicity, but of order 10,000 degrees. So it's 5 times hotter. Planetary nebula nucleus, by comparison, goes to much, much higher energy. So the mean photon is going to be higher. Expressed as a temperature, you can see it's a quarter of a million degrees. And then an AGN is the hardest of all, extending out into the X-rays. This has this radiation field has a temperature of 30,000 degrees. So you're ejecting new electrons into the plasma at these high temperatures. That energy is being shared with the thermal electrons that create the lines we see by collisions. And then the whole thing recombines and starts all over again. So next time we're going to get into actually doing some calculations involving the temperature and see some of this physics in action. See you then.